agriculture, etc. And lastly, and so here's the class outline. I want to start with a short kind of anecdote from an experience that I had living in Guatemala, and how the threat of chemical pollution was going to affect small community. And then I want to take a look at two. There's thousands of different types of man-made chemicals. And obviously in an hour-long class, we're not going to be able to look at all of those, but I want to take kind of a focus on two of the most kind of pervasive and perhaps two of the different types of chemicals that generate most headlines today in the news, and that are very worrisome. So one is the PFAS sort of chemicals. We'll talk about what those are. And then also all of the whole suite of agrochemicals that are used in industrial agriculture today. And then after we look at kind of what are the pervasiveness of the toxic buildup in our in our environment, in our communities, and also in the human body, I want to look at why this is happening, right? What are some of the underlying factors that cause this dramatic increase in chemical pollution? And this is something, again, that has taken off in the past 5, 6, or 7 decades. It's something relatively new. It's a consequence of modernity, of the Industrial Revolution, of the modern day world we live in, right? So we're going to look at the issue of the growth-based economy and how resources and energy are becoming harder and harder to access. And what does that portend for rural communities, for communities who still have a fairly intact resource base? We're going to look at how global demand for resources, for energy to fuel this growth-based economic system in which we live is creating ever greater conflicts, environmental conflicts, social conflicts in rural areas, right? And then lastly, I want to make a couple connections to how this issue of chemical pollution is directly affecting those of us who work in the idea of development, right? I want to talk quickly about what is a progress trap, following the work of an author I like called Ronald Wright, and also talk about how to rescue this idea of the precautionary principle. That's kind of the outline of the class today. But let's start real quick with an anecdote. When I was fortunate enough to work in the mountains of Guatemala in the Ixil territory, the Ixil people are an ethnic group of the Mayan people that live in this beautiful, beautiful mountainous region in northern Guatemala. And like most indigenous people, they have kind of a collective land tenure. So they have this. Everybody has, their own plot of land where they live and where they grow their corn and beans. But then around, these kind of use-based agreements, there's an enormous area of collective land. So forests and pasture land, collective access to water. And so above the community of Neba, there's these beautiful mountains, and there's the forest was always kind of managed as this collective resource. People would take their animals to forage in the forest. People could cut down, tree limbs for firewood. It was where all of the water, came from these springs. It was protected, kind of in a communal arrangement by the Ixil people. All of a sudden, when I was living there in about 2012, one day there was about 3 or 4 helicopters that landed in the middle of this pristine, beautiful communal forest. And the community saw the helicopters, and everybody they sent a commission to see what the heck was going on, and they went up there, and there were some executives from a North American mining company who had claimed that the Guatemalan government had given them access to create a barite mine. And the people were just all of a sudden confused. Like, first of all, who gave you this access? This land is ours. How do you know that there's barite here? So eventually what they did is they told them, we need you to come and sit down and explain who you are, how you supposedly got these arrangements, and what you want to do. And so there is these really, really tense moments of negotiations with essentially the mining company they were interestingly open, and they said, look, we have satellite images that show that underneath your mountain here is one of the largest sources of barite. And people had, what is barite? And so barite is a mineral, a rock that has some uses for consumers. It's used in like X-ray machines, but it really became there's a high demand for barite right now. because it's one of the main things used in fracking fluid. And for those of you who don't know what fracking is essentially all of the oil and natural gas that our world depends on, the motors of industrial civilization, is getting harder and harder to access. All of the very simple, easy to access sources of fossil fuels have been used up, right? The stuff that's kind of just below the surface of our soil is gone. And so what energy companies are having to do are having to go deeper and deeper into the Earth's crusts, into the bellies of the Earth. And to do that, they have to what they call fracture, the bedrock, these layers of very, very thick rock. And underneath that rock, there's more deposits of gas and oil and all these things. And in order to fracture that rock, they need heavy, heavy what they call fracking liquid. And barite, which is a type of a rock that is very, very dense, is ground down and used in this type of fracking fluid to fracture the rock, open it up, and allow these companies to access these enormous sources of oil and gas and other certain types of minerals that are below the Earth's this thick layer of rock. And it was interesting because in the small community where I grew up in the United States, there was issues around fracking. There were these major companies that were doing that, and there was all of this kind of community resistance against fracking because it was contaminating groundwater, it was contaminating the aquifers. There's all these videos of people who turn on their water in their homes, and they light a lighter, and all of a sudden, boom, the water goes up in flame because all of this contamination from gas that's seeping into the aquifers. And there's a lot of very, very strong opposition to fracking where fracking occurs. But then you think about, for fracking to occur, it needs all of these other resources. It needs barite, right? You need to, and fracking fluid is made up of like 10 or 12 different types of chemicals, different types of minerals and elements. And all of these minerals and all of these elements come from somewhere, right? And that's one of the things that's fascinating when we think about the global economy that we live. There's a really fascinating essay that was written back in the 1970s, I think, about a pencil, right? You take just any pencil and you think about all of the different elements that are made in something of a pencil. Where does the wood come from? Where does the graphite lead come from? The metal that holds the eraser, the rubber that is made up of the eraser. And in this essay tries to take a look at where all of these elements come from. Everything is mined and is mined from a certain place. Everything is grown, mostly in industrial kind of capacities. And if you think about something as simple as a pencil and all of the global supply lines that go into that, it's an enormous, complex kind of operation that occurs for something as simple as a pencil. And the same thing happens with barite, for example, or with fracking. Obviously a pencil is a relatively simple product. When we get into things around more complicated products, such as the computer that I'm talking to you on today, all of the different metals and all of the different rare earth metals and all of the plastics and all of the different components that go into that, it's an incredible long supply line. And while I was working in Guatemala, I started thinking, there's a lot of like media attention directed towards communities that are directly opposing, for example, the fracking industry. They don't want fracking happening in their community. They don't want their water supplies to be contaminated. But nobody thinks about the rural indigenous population in the mountains of Guatemala, that in order for that fracking to occur, barite needs to be mined and all of these other minerals and chemicals and elements that require fracking fluid and everything. And it just shows how incredibly complex and intense our global industrialized economic system is, right? And that was something that kind of woke me up to to this issue that chemical contamination is bound to occur in this complex system where so many things come from so many different places. I don't want to come back to that example, but I just wanted to start with that to show how pervasive chemical pollutants are through the mining industry, through these complex supply lines. But yeah, before we get into kind of the connections to development, like I said, when we talk about chemical pollution, I could talk for an hour about all of the different dangers of barite mining, for example, which is one chemical. And so, we brought in when I was living in Guatemala, we brought in some experts to talk with the community about, what has happened in barite mines in other places. And we went to visit a community in southern Mexico that had a barite mine, and how people had lost access to water because the big mining companies had diverted rivers so that they could have more water to extract the barite that they need to refine it. And that's just one chemical, right? So, or one element, one type of mining. But I wanted to kind of to show the threats of chemical pollution. I wanted to take just two kind of examples. And the first one are what we refer to in English, which are called PFAS or PFAS chemicals, also known as PFOS. And a lot of people, we might have heard of that term, but we don't really know what it is. I'm not a chemist, and I don't know exactly what the chemical composition of these chemicals are, but it stands for polyfluoroalkyl substances. That's what PFAS stands for, and it's a group of over 4,000 human-made chemicals. PFAS are ingredients in various everyday products. For example, they're used to keep food from sticking to packaging. So pretty much every food stuff that you purchase in the supermarket, whether it be canned food or boxed food or food that's in a plastic bag, all of this packaging has these PFAS chemicals. It's also used, for example, in most of the cookware. You go to the store and you buy a pot or whatever it might be, and all of the non-stick stuff that they have to supposedly make it easier to cook is filled with PFAS chemicals. Most of the clothes that are made by the textile industry include different types of PFAS chemicals. They put it on carpets, on furniture. It's used by firefighters, foam. It's essentially this industrial chemical that makes things more durable, right? It's used in almost every type of adhesive. If you ever used a glue or different types of, tape, it's on that. And there's thousands and thousands of different industrial applications and consumer applications of these types of chemicals. And starting back in the 1970s, when they developed these PFAS chemicals, they were heralded as this great invention, right? They're going to make our lives easier. Now we can, if our children accidentally spill, a little bit of juice on the carpet, our carpets won't get stained because they have these miracle chemicals. We can cook and we don't have to worry about our fried eggs ruining our frying pans, because now we have these special chemicals that make it easier for us to cook with. But then, all of a sudden, about 10-15 years ago, they started to find out that these chemicals don't break down. They are persistent. Most chemicals, for example, if we naturally occurring chemicals are released into the environment, and they break down over time. Bacteria and fungi and all of the different microbial life that exists in the soil, in water, in the natural world, eventually break these things down. But one of the things that's interesting about the PFAS chemicals is that they don't break down. They accumulate over time. There's something unnatural about them, that they are so persistent that all of these chemicals that were released, starting back in the 1970s, they're still there. And even though they're a small amount, since they don't break down, they accumulate over time. And now, as people have found out that these PFAS chemicals are starting to accumulate in our soils, in our waters, and in the human body, now we start to think, well, what are the effects of that, right? And they found that PFAS is pretty much in everybody's blood, right? Not just people who work in these factories, not just people who actually consume these products, but even remote indigenous tribes in the Amazon have been found to have fairly moderate levels of PFAS chemicals in their blood. And that's because PFAS chemicals are now in the atmosphere. Even the air that we breathe, there's an accumulated presence of these chemicals that do not naturally break down. After decades of development and all of the applications in thousands of everyday consumer products, we now find out that PFAS chemicals are linked to a huge range of health risks. For example, we know that PFAS causes cancer. both kidney and testicular cancer. It causes hormone disruption, liver and thyroid problems, interference with vaccine effectiveness. It causes all sorts of reproductive issues, including the inability for people to get pregnant if they want to, abnormal fetal development. And one of the things that's fascinating is that all of these things that we find out now about what happens is that they're not going to go away. Our grandchildren are going to have to deal with all of these negative effects of PFAS in the environment because we don't know how to get rid of them. Just one other example, we talked about the issues of fertility. There's lots of studies going on that most people talk about the need to reduce the human population. And I listened to a fantastic presentation a couple months ago by a leading fertility specialist. And she said that, obviously our population has exploded from 1 billion people about 150 years ago to 8 billion. And it's almost expected that that's going to increase to 10 billion. But she said, now what we need to start thinking about is how do we maintain a decent level of population? And one of the things that they've been determining is that fertility rates, for example, amongst men, sperm counts have been falling 1.2% per year between 1973 and 2018. And most scientists believe that PFAS accumulation, this chemical contamination, is one of the main causes of this drastic decline in sperm counts and in male fertility. If we were to continue this, so from between 1973 and 2018, it's 45 years, male sperm counts have been dropping by 1.2% each year. If we continue that trend for another 50 years, and if nothing is changing that trend, then it's going to be impossible for humanity to naturally conceive children. And so this fertility specialist is saying is that, look, this accumulation of toxic chemicals in our environment is causing, this almost existential threat to humanity. We might not be able to conceive a new generation because of the amount of chemicals accumulating in our bodies. And the other issues with PFAS is that it's incredibly, because of the ability of these chemicals to accumulate in soil, in water, in the air, in every aspect, in the human body. We don't know how to get rid of PFAS that's in our body. The cost of trying to remediate the damage, the contamination, is unthinkably high, right? For example, if you have an oil tanker, that there's an oil spill somewhere in the Arctic Ocean or wherever that might be, generally, international courts try to hold responsible, these massive oil companies to remediate the damage, and they have to spend billions of dollars to try and clean up the oil spill. And there's different techniques that they can try and do. Obviously, there's lots of damage that in harm that can't be repaired, all of the marine life that's going to be affected. But generally, there is a way to estimate the cost of cleaning up, an oil spill, for example. But when it comes to PFAS remediation, the cost of that is incredible. 3M is one of the main chemicals, one of the main companies that has been responsible for the development, manufacture, and the industrial and consumer uses of all of these PFAS chemicals. And recently, they were sued by the state of Minnesota, which is where they have their main factory. And they're saying, look, you guys have been pouring into the environment, into our state environment, all of these chemicals. And there's lots of information that the company knew that these chemicals were not breaking down. They knew that there were certain health risks associated with that, but they were also extremely profitable. And so despite the risks, they said, oh, we're just going to continue along. And so they were sued, and the court said that PFAS over the next 10 years has to spend $10.3 billion to remediate PFAS contamination in Minnesota, which is one state in the United States. $10.3 billion to clean up the known places where PFAS have been accumulating in the environment, mostly around the factories and places like that. However, there's other studies saying that if we really tried to put a dollar amount on how much it would cost to clean up, to try and get rid of the PFAS contamination worldwide, it would cost 17 trillion US dollars each and every year. What's that? It's not possible. That's comparable to like the world GDP every year. So we're not going to be spending, everything we make just to clean up just one class of chemicals. So the economic cost of chemical pollution, especially with certain types of chemicals that accumulate in the environment, is so high that it's not going to happen. Essentially, we have created a whole suite of chemicals that are used in non-essential everyday products. For example, you can use the Teflon coated PFAS contaminated cookware, or you can use a aluminum pot or a cast iron thing. So it's not necessary. Most of the applications of PFAS chemicals are essentially just profit making schemes for these companies. They're not creating anything that is absolutely necessary to humanity. They're kind of frivolous products that people think are useful, that make our lives a little bit easier, again, because we don't have to, I can spill this juice on my shirt, and all of a sudden I don't have it won't stain. I guess that's a unique application, but at what cost, right? We've released these chemicals around the world to the point that remote indigenous tribes in the Amazon rainforest, those who have never come in contact with all of these industrial everyday consumer products, they also have PFAS contamination in their blood because it's now in the atmosphere. We find out that these chemicals don't break down naturally. There's no way to get rid of them, and that they're killing us, and that it's impossible and too expensive to clean them up. PFAS contamination is an issue, like I said, that is going to affect our lives, the lives of our children, the lives of our grandchildren, because up till now, we don't know how to get rid of them. And again, that's just one class of chemicals, right? Let's take a look at one other class, agricultural chemicals, right? Which is used in pretty much every type of farming around the world. I've talked a lot in past classes about organic and traditional agricultural methods and how these methods were able to produce healthy, diversified foodstuffs for local populations. But starting back in the 1940s, 1950s, the Green Revolution started, and there was this movement amongst mostly the United States and Europe, and other industrialized developed nations that had all of this technology that they wanted to use. And they said that we need, the population is growing and traditional organic farming methods are ineffective, are inefficient. And what we need is this green revolution, this use of chemical inputs, of chemical fertilizers, chemical pesticides, and that's going to allow us to drastically increase the yields of farming. And that's how we're going to save the world from famine. We're going to save the world from itself. And so sure, in the first couple years, in the first couple decades, when these miracle fertilizers were applied to fields, there was a drastic increase in productivity, right? Whereas a corn farmer here in Central America used to maybe get, let's say, 10 bushels of corn per acre. Now they got 100 or 20 or 30 or 40 bushels of corn per acre. And so there was touted this miracle thing. I just take this chemical source of nitrogen and I throw it on the fields, and all of a sudden I get these bigger crops. If we fast forward 75 years, what has happened from this green revolutions? Well, today, over 1 billion pounds of pesticides are used in the United States each year, and approximately 5.6 billion pounds are used worldwide. 5.6 billion pounds of chemical fertilizers are used each and every year. Now, chemical fertilizers, most of them, and also chemical pesticides, do break down in the natural environment much faster than PFAS, for example. Some agrochemicals will break down after a month, some after 6 months, some after a year. It depends on the environment. But the issue here is that these aren't chemicals that we use once and then we never use again. If we were to use agrochemicals once and not use them again ever again, they would break down fairly quickly. But the problem is that most farmers around the world are so dependent on these agrochemicals that the use of them is growing year after year after year. In 1965, talking about fertilizer, the consumption of nitrogen fertilizers stood at 46.3 million metric tons, which is a lot. By 2021, this amount is almost 200 million tons of fertilizer. And we're going to talk about this. One of the issues with agrochemicals is that as agrochemicals, as this industrial mode of agriculture has kind of extincted all of the traditional methods of maintaining fertility, all of the traditional methods associated with traditional farming, where wastes and manure were recycled back into the soil. People have lost that ability. And so once you use chemical fertilizer, the first year, you might only need to use a little bit, but then your soil continues to degrade and you have to use more the second year, more the third year, more the fourth year. The same with pesticides. You might use it one year and it's amazing that you kill off all of the bugs that were eating your cabbages or your corn or your wheat or your rice. But then you find out that the next year there's more of those bugs. Then the third year there's more, and then there's more, and there's more. It's because these pesticides disrupt these natural cycles of how nature takes care of itself, of how certain bugs are regulated by other bugs. And all of a sudden, when you create this kind of genocide of insect life, you have to use more and more and more of these agricultural chemicals. So now we're using 5.6 billion pounds of pesticides and almost 200 million tons of fertilizer every year. And in order to continue to grow food, we will need to continue to use this. Glyphosate, which is one of the most common herbicide or weed killer, is one of those widely used agrochemicals around the world. In the United States, the Federal Health Agency tested 1,600 urine samples of adults and children from different parts of the country, from urban areas to rural areas, people who live in the middle of nowhere, and they found out that 80% of adults had detectable levels of glyphosate in their urine. 87% of children of 87% of children had that in their urine. They found that pretty much every woman who are lactating, women who are breastfeeding, almost every sample of breast milk contains glyphosate. So when mothers feed their children, they're feeding them glyphosate along with all of the nutrients that come with breast milk. Glyphosate is used in food crops, pretty much every type of food crop possible, and it's found virtually everywhere in the food chain. There's been other studies that show if you go to a supermarket and you just by random pick out any product and you test it, there's going to be residual traces of glyphosate in that food product. And then all of a sudden, about 10 years ago, glyphosate was found to be a cancer-causing chemical. It's like, oops, it was great. I mean, we sprayed this on our fields and then we didn't have to deal with weeds. And it was considered for a long time to be relatively healthy until it wasn't. And so now we have this situation where farmers everywhere are absolutely dependent on using herbicides like glyphosate. We don't know how to farm without that anymore. But now we find out that when we use that, it's accumulating in an environment, it's affecting our bodies, and it's causing all of these different types of cancers. Similar to PFAS, there's been certain attempts to try and put an economic cost on what are the costs of pesticides. And one study found that the hidden cost of pesticides equals at least $140 billion annually. All of the costs associated with the medical costs, with the costs of trying to clean up the water that's contaminated, the costs of cancer treatment for people who use these agrochemicals and then find out that they have lymphoma or all the other different types of chemicals. The cost of that, the hidden cost of pesticides, is at least $140 billion each year. Globally, the sale of pesticides is 60 billion in 2020. So the externalized costs, all of the negative effects, the externalities of using these agrochemicals are at least 2 to 3 times higher than the sales itself, right? And these are costs that are not factored in, right? Nobody pays that. Nobody is telling Monsanto and Bayer and all of these big companies that they have to pay all of these hidden costs. In addition, and like I said, after decades of saving the world from famine, and saving is something we could certainly question, industrial agriculture inputs such as glyphosate, such as pesticides, such as nitrogen fertilizers, industrial agricultural inputs have ruined topsoil, contaminated watersheds, ruined traditional agricultural knowledge, and left us facing major questions regarding how we're going to feed a future 10 billion population. Like I said, now that people are using ever greater amounts of agrochemicals, the amount of nitrogen fertilizers that you need to apply year after year is increasing. The amount of pesticides and the strength of those pesticides that we have to use is becoming ever more and more. And to the point that today, like I've talked about in other classes, many major organizations are saying this model of chemical intensive industrial agriculture cannot continue. It's simply too expensive. There's too many hidden costs. There's too many health effects. There's too many environmental effects. And so now they've talked about transferring the whole issue of food production into laboratories, right? We can't continue doing as we're doing. So we're gonna get rid of farmers and hope that laboratories will be able to create some sort of synthetic foods to feed our growing population. Um, so those are just two examples. Like I said, agrochemicals and PFAS pollution, again, are just two different types of chemicals. There's an enormous amount of chemicals, and all of them have very similar effects. We release them into the atmosphere, we release them into the soils, into the water, and only afterwards, only after, several decades of having used them, we start to understand the accumulating effects, the effects on their environment, the effects on the human body, the effects on health, the effects on well-being. But why is this happening? Why does this, what are some of the underlying factors that cause this drastic increase in chemical pollution? One is the issue of economic growth. The growth-based economy is going to continue searching for new ways to expand the global economic sphere. And one thing that's very important to understand is that economic growth is always tethered or connected to more resource use and more energy use, almost on a one-to-one basis. If our economy grows, that means we need more resources, right? If our economy grows, we need more energy inputs. And there's a lot of people that talk about decoupling economic growth from resource and energy use. And it's basically a falsity, right? So you might say, oh, so now that so much of economic productivity occurs through the internet, we're not necessarily. So, for example, instead of having a class, an in-person class like today, where each and every one of you would have to take the bus or drive your car to the physical car space, now that it's happening online, it's kind of considered to be resource free. But that's not true, because all of us are using a computer. We're using energy for the Zoom meeting. There's an enormous amount of energy inputs from all of the data centers that are required for this. So the resource inputs and the energy inputs might change, but as the economy grows, all of the different types of resources we use also continues to grow. Nate Hagens has written great, fantastic about this, and he did the maths, and he said that if the global economy continues to grow at a modest 3.0% per year, which is what most governments around the world hope for, we will consume as much energy and materials and resources in the next 30 years as we did cumulatively in the past 10,000 years. Think about that, right? What are the chemical, what are the environmental and chemical effects of growing the amount of resources and energy we use at this rate? How much more chemical contamination is there going to be based on this growth-based economy? Another important aspect to think about is the issue of EROI, which means energy return on energy invested. This statistic, this kind of ratio of our most important fuels is declining, and most renewable and non-conventional energy alternatives have substantially lower EROI values than traditional conventional fossil fuels. What does this mean? That means that, before, when we wanted to extract oil or coal or natural gas, we used 1 unit of energy. Let's say we used one unit of energy, and we got 100 units of energy out of that. Today, that's gone down to about 10 to 1, right? So now the vast majority of the energy we use, whether it be solar energy, whether it be wind energy, whether it be fossil fuel based, the vast majority of energy we use is to extract more energy, right? And so, as the energy sources, like I mentioned, like fracking, all of the easy to access sources of oil and coal have been used up. Now we need to go deeper. We go into the deep seas. This is a picture of the tar sands in northern Canada. So all of these really impure sources of oil and coal that are still extractable, but it takes an enormous amount of energy just to extract that. And so all of the rural communities who happen to live where these places, where these mines be for any type of resource, for any type of energy resource, are going to be affected because it's getting harder and harder to extract the resources we need to continue to push this global economic growth-based system. One other example I think is fascinating is that there are billions and billions of tons of copper in the Earth's crust, but the amount of copper that we get per ton of material removed has declined by a factor of 100. For example, 200 years ago, there were places in the United States where there was a 40% ore grade of copper. That means that if you took out 100 tons of material, of soil, of rock, you had about 40%, 40 tons of that was pure copper. That was in these very, very high ore places. On a global average, it was about 4%, right? So you would take a 100 tons of mining material, of rock and soil and water, and you would get about 4 tons of copper. Today, that's 0.4%, right? So it's getting harder and harder to access something as essential as copper. And that's why you have these mines. This is one of the world's largest copper mines, right? And so when we talk about the green energy transformation, the electrification of everything, as we move away from fossil fuels, we're going to need an enormous amount of wind turbines and solar panels and all of these other things, right? And all of this is going to require materials. And copper, for example, is one of the main materials that we're going to need. And because copper is becoming harder and harder to access, what we're going to have to do is dig deeper and deeper into the earth, create larger and larger mines, right? And that's important to understand. We need bigger trucks, more water, more energy. The transition to renewable energy future does not reduce demand for overall energy and resource use. That's very important to think, right? As we make this green energy transition, no one is talking about using less energy, using more efficient sources of energy. No, we're going to continue we want to just kind of transition over, but we want to continually use more and more energy, right? And so, for example, the whole issue of solar panels, right? To make solar panels requires an enormous input of resources and of energy. And I mentioned this in a past class that I think is really important to understand that one recent study found that 80% of solar panels today are made in China, and they're made in factories that are powered by coal. So the embodied energy footprint, the carbon footprint of a solar panel over its 20 or so years of lifetime is actually higher than natural gas, because the factories that are creating these solar panels create an enormous amount of carbon emissions, right? And so, as we use more renewable energy, if there's nothing that questions this whole issue of growing demand for resources, a growing demand for energy, then we're always going to come up with problems, right? And so today, all of this green growth, all of these renewable energy technologies that are continuing to grow are going to need an enormous demand, are going to lead to an enormous demand for lithium, for cobalt, for copper, for iron, for steel, for all of the other rare earth metals that are used in renewable energy technologies and digital technologies and computers and cell phones and AI and data servers and these data centers. If we continue to want to grow, there is going to be increased demand for all of these things. What does all of this have to do with development? As the economy grows, and as resources and energy sources become harder and harder to access, the obvious and most inevitable effects will include: one, further displacement of indigenous, peasant, and other rural communities in order to access the resources on their lands, right? If we need ever more copper, ever more cobalt, all of the rare earth metals, because everybody wants to have a new cell phone every year, then the people who still live in these pristine ecological places, and almost always it's the indigenous and land-based peoples, those who have protected their landscapes, like the indigenous people in Guatemala that I mentioned, they still have barite there, and they still have these, lots of resources because they've protected that land, because they live off of that land, because they understand the value of an intact and healthy ecosystem, of protecting the forest. But now, these companies have these satellites flying in outer space that are able to look down in the earth and say, oh, look, there's barite. We need barite because we need to frack. We need to frack because we need more energy. We need more energy because we need to produce solar panels. And so there's going to be an increased demand for the resources that are mostly found in these pristine ecological spaces. If you look at the statistics at the amount of illegal mining and logging in the Amazon rainforest, that's because that's where the resources are left, right? So more displacement of indigenous, peasant, and other rural communities. The pollution, environmental destruction, and toxic residues from this extractive economic model will continue to drastically affect the remaining place-based peoples and their lifestyles. Thus, traditional, vernacular, we used that word last week, and truly sustainable models of human habitation in place will become harder and harder to sustain. Those of us who work in the development industry are going to find in the coming years that there's going to be enormous amounts of pressure from corporations, from governments, from big businesses wanting to extract more and more resources. And when communities say no, when they say, no, this is our place, we want to protect it, then all of a sudden you're going to be coming up with these very serious kind of social, the militarization of these spaces. In some cases in Latin America where there's not good governance, on a national scale, there's going to be these, a lot of militarization of these places. There's going to be, very serious conflicts related to that. And then lastly, another reason why I think this is happening, of why chemical pollution continues to increase in the environments and around the world, is due to this issue of progress trap. A progress trap is a condition human societies experience when, in pursuing progress through supposed human ingenuity, we inadvertently introduce problems that do not have the resources or the political will to solve for fear of short-term losses in status, stability, or quality of life. Ronald Wright wrote a fantastic short book that I would recommend called A Short History of Progress, and he talks about progress traps. He says that a progress trap refers to innovations that create new problems for which the society is unable or unwilling to solve, or inadvertently create conditions that are worse than what existed before the innovation. And I think this idea of progress traps affects the whole issue of the development industry. In fact, that's one of the reasons why my wife and I decided to leave the development industry, because I think we don't think deeply enough or long enough about some of the effects of the things that we want to incorporate. So if we again go back to the green revolution example, right? We used this green revolution because it was going to, all of these agrochemicals were going to boost agricultural productivity. At the same time, it was going to boost the profit margins of these companies, right? And so we think only about the short-term gains, right? When we think about, but then once everybody starts using that and everybody becomes addicted to using chemical fertilizers, chemical pesticides, and then traditional farming methods are lost. People forget about how to recycle residues and excrement and all of these natural fertilizers to maintain soil fertility. We forget about that, and then we're stuck. We're in a progress trap. We can't imagine going back to a different way of life. We can't imagine what life would be like. And so all of a sudden we create worse conditions, right? So if you look at industrial farming, all of the chemical residues that are associated with that, we're stuck in a progress trap. We know that we cannot continue all of the chemical contamination associated with industrial farming, but we don't know, what to do without that. The conditions today are worse because of the green revolution than what existed before the innovation, but we're stuck, right? Real quick, just two more slides. Aldo Leopold was one of the original kind of ecological thinkers back in about a century ago, and he said that to keep every cog and wheel is the first precaution of intelligent tinkering. Since the Industrial Revolution, we have heavy-handedly tinkered with the natural world in the most unconscious, haphazard way, and chemical pollution is one of the most obvious effects, right? So trying to adapt this mentality, I'm not saying that scientific innovation doesn't have a place. Of course it does, right? But we need to learn how to think long, take the long view, think long term about the effects of our tinkering on the natural world. And also, I would say to think about the effects of the remaining place-based peoples, people who still live off of the land, indigenous communities, rural communities, people who live in marginalized situations who depend upon the resiliency of the land in order to survive. And then lastly, the precautionary principle is something that has kind of been tossed to the wind. The modern day industry and science no longer thinks about that, but I think that one of the ways that we can deal going forward with all of the threats from chemical pollution is to rescue this idea of the precautionary principle. And here are two quick definitions. One is the principle the precautionary principle is the principle that the introduction of a new product or process whose ultimate effects are disputed or unknown should be resisted. If a product, an action, or a policy has a suspected risk of causing harm to the public or to the environment, protective action should be supported before there is a complete scientific proof of risk, right? We should never have been playing around with PFAS chemicals, right? Knowing that they probably would accumulate in the environment. Even though in the 1970s, we might not have known that they caused thyroid problems and fertility issues and cancer. There's a certain responsibility towards everyone who lives in the world today and towards future generations and to all of the creatures with whom we share the earth to take seriously this responsibility, right, of the precautionary principle. And I would say that that's something that we need to, that's been thrown to the wind. Nobody thinks about that anymore. And if we worry about the ability to leave a world, an ecosystem